All right, sorry for the delay. My name is Craig Hardgrove. I'm an assistant professor at the School of Earth and Space Exploration at ASU, and I'm the PI of LunaH-Map, which you can see here is an EM build of the spacecraft. We are manifested on SLS Artemis 1. Some of the details on the mission are on this slide. We were selected in the very first simplex call back in 2015, which is a little bit differently structured than the current simplex call. But the spacecraft is a little bit bigger than a 6U, and our science objective is to map the lunar south pole hydrogen enrichments and resolve PSRs and map hydrogen at scales that would be useful for landing sites, as well as resolving some outstanding unknowns about the evolution of volatiles at the south pole of the moon. We also have a few technology objectives. We need to demonstrate deep space navigation with a small spacecraft, as well as operations, and we are using a very small ion propulsion system, which I'll show you a picture of a little bit later. I toyed with saying on a itsy bitsy sat. I'm not sure that small sat really is the appropriate term for the size of our spacecraft. The spacecraft is about the size of two large cereal boxes put together. The solar arrays, when they're extended, are about 1.5 meters long. So we're a very small satellite, and the propulsion system is about the size of a tissue box sitting on your dining room table. So everything is very small, but the exciting part about this mission is if we're successful, we will enable a lot of these very small technologies to be used on future NASA missions and be co-manifested like we are on SLS, which has a primary mission, but we will demonstrate that you can execute a meaningful scientific mission on a very small satellite that hopefully can be accommodated easily on larger scale NASA missions moving forward. So like I mentioned, we're using a neutron spectrometer, and this is a previously acquired map of the epithermal neutron counts at the south pole of the moon turned into microgram per gram H content or hydrogen content. And the unique thing about neutron measurements is that they're sensitive to the bulk hydrogen distribution down to about 1 meter. And the meaningful thing about LunaH-Map is that we'll collect unambiguous data at the south pole of the epithermal neutron counts, in that we are not using any collimation like is used on Lunar Reconnaissance Orbiter. The neutron detector will just count the neutrons that leak from the moon, and we will achieve resolution of the permanently shadowed regions by flying very, very low. I'll show you the altitudes that we'll achieve throughout the mission later. But you can see that the south pole here with Lunar Prospector is identified as being enriched in hydrogen. You can see that the regions where the hydrogen is enriched appear to be concentrated around the permanently shadowed areas. But depending on how you bundle up some of the hydrogen, it could be between 200 parts per million and up to 40 weight% if it's in a very small confined region. So part of the goal is to really help resolve and put some meaningful constraints on the spatial distribution of the bulk hydrogen at the south pole. And here's just an overview of some work that you're probably all familiar with. This was done by Rick Elphick in 2007, just using a Pixon reconstruction and demonstrating that the hydrogen enrichments, if they're due to completely within the permanently shadowed regions, can reach up to 1,000, that should say micrograms per gram, sorry, on that scale, or up to a half a weight% within some permanently shadowed regions. If you look at the LunaH-Map, that's quite similar. You will see some differences between this map as well as the previous map I showed from Lunar Prospector and the Pixon reconstruction maps. And then if you move forward, we of course had L-Cross, which shows that there's about 5 weight% water that was kicked up in a plume of regolith. And so at small scales, it's somewhat unknown what the bulk distribution of hydrogen is. And so LunaH-Map will help to put some additional constraints on that by acquiring data at the 20 square kilometer scale and resolving some of the permanently shadowed regions at the south pole. So here's some additional information about the science goals that we hope to achieve. We're building on some of the data that I just showed, as well as new data that's been collected from Dawn, which was recently presented to AGU by our co-I Tom Prettyman, showing that a combination of sublimation and impacts can control the distribution of subsurface ice. LunaH-Map's orbits will cover the majority of the South Pole at poleward of 75 south. And so we'll be able to make maps of the ice distribution both within and external to permanently shadowed regions. So we can address questions about whether or not there are thick ice deposits potentially delivered by ice-rich asteroids or comets that may be pervasive outside of PSRs, and those could be due to impact gardening, which vertically redistribute the ice and bring it closer to the surface. So having these high-resolution maps will contribute to a lot of the science questions about volatiles at the South Pole. And then I'll spend the rest of the talk just telling you a bit about the mission. Here's some of our trajectory design. So in the spaghetti plot on labeled number 1, you can see the Earth, and then the orange line is where we're deployed from SLS. We execute a relatively long maneuver with the ion propulsion system to swing by the moon, and that swing by puts us out at the weak stability boundary, L2 between Earth and the Sun. And at that point, we turn back around and meet back up with the moon. And you can see that in number 2, we are weakly captured by the moon. We're then more strongly captured, and then we enter a spiral down orbit where we'll maneuver into the science phase, which is shown in number 3. The science phase has about a 4.5-hour period. And so we're only making meaningful neutron measurements over the South Pole for about 20 minutes. And the remainder of the science orbit is devoted to spacecraft maintenance, downlink of our telemetry data and science data, and any maneuvers that need to be performed at Apollon with the propulsion system. And the trajectory solution for LunaH-Map has been published in AIAA paper that you can look up there. And these are what the ground tracks look like over the South Pole. May have evolved some, but we get great coverage over the areas near basically poleward of about 85 south, and it trails off a bit. And I'll show you what these look like in terms of how these will turn into neutron data products a bit later, just by going through one of these example orbits. So this is one ground track over Shoemaker. In red, we've labeled the PSRs at the South Pole of the Moon. And this is one that cuts right through Shoemaker. And you can see PSR contribution to the neutron signal over Shoemaker reaches, I can't see it because of the little slide, but it's over 60 to 70% within that orbit. And you can see the altitude for that orbit in the bottom right. And if we go to the next slide, we show all of the altitudes, the minimum altitudes achieved for each orbit. You can see in some orbits we dip down to 7 or 8 kilometers above the terrain. And on some other orbits, we're only about 15 to 20 kilometers over the terrain. And on the image on the right shows how that turns into contribution to the epithermal neutron signal from the permanently shadowed regions. So this tells us that for the larger permanently shadowed regions, we're certainly resolving them. And you can additionally populate the South Pole permanently shadowed regions with example hydrogen distributions in microgram per gram. So some are labeled here. We have populated the background distribution with 50 micrograms per gram, which is labeled B in the bottom left. And you can see the other permanently shadowed regions labeled there with some example populations from some of the literature and observations. And this is a noise-free map. Obviously, this is not what we're going to see with the instrument, but just to show the how the epithermal counts would vary for our science phase in a noise-free environment. And then we can introduce noise across the 30-day mission. And we can see that most of those regions are resolved, although we get pretty noisy out of equatorward of 75 south. And then over the course of our 282 orbit, almost 2-month mission, we're doing a bit better job of resolving the permanently shadowed region. So just to summarize some of the mapping capabilities, we can detect some of the expected hydrogen contributions in the permanently shadowed regions. While the PSR are resolved, we don't fully, the full contrast isn't achieved. That means that the neutron signal extends a bit outward of the topographic feature that identifies the permanently shadowed region. And these low altitude measurements do enable high spatial resolution mapping of the permanently shadowed regions and the surrounding areas of the South Pole. And this will enable verification of the results from previous missions, Lunar Prospector, Neutron Spectrometer, and LEND, and hopefully provide some additional constraints on how volatiles at the lunar poles and other airless bodies evolve over time. So a bit about our hardware. This is the neutron spectrometer, which was developed specifically for this program. It's comprised of two separate detector units. Both are covered in a shield of gadolinium, which make the detector sensitive to epithermal neutrons. A bit more about the detector here. Each detector is a 2x2 array of a El Paso light scintillator, CLYC. You can see the formula. We get about 200 square centimeters of detector area, and the whole total detector is about 3 kilograms, uses about 10 watts of power. All the onboard data processing is done using onboard FPGA. And then the sensor itself, each sensor is connected to a digital signal processing board as well as an analog high voltage board. And each module looks like that. So the sensor head is comprised of a 2x2 array of those modules that you see in the middle. The graphic on the right shows the intrinsic efficiency of one of those modules for the epithermal neutron region of interest. But for future small-sat missions that may be interested in a neutron spectrometer, this detector can be modularized, so we can use up to 4 modules on a single electronics board, or down to 1 or 2, and you can rescale the form factor of the modules to fit the mission profile. And this is the calibration team at Los Alamos in the Neutron Free and Air facility, where we calibrated the neutron spectrometer, which you can see there, mounted to a rotational stage on the right. You can't see in this image, but there's a calibrated neutron source, which we moved. We moved the spectrometer forward and back away from the calibrated neutron source and rotated it so we can quantify the spatial sensitivity of the sensor. This is the same location that the neutron spectrometer for Lunar Prospector, as well as the gamma ray neutron spectrometer for the Grand mission, the Dawn mission, the Grand instrument, was calibrated. Here's just a quick look of the spacecraft and all the components. We weigh about 14 kilograms when we're all buttoned up. The solar arrays use 90 watts, beginning of life. The propulsion system is provided by Busek. It uses about 65 watts when maneuvering. We use the IRIS transponder, which is used on Marco, as well as is being used on several of the other CubeSat missions that are manifested on Artemis 1. And I wanted to finish up with just some photos of our flight hardware, which we have all in-house here at ASU. They've all been delivered. These are our solar arrays, this is during a deployment test in February of last year. This is the IRIS radio, which was also delivered in February of last year. The BIT3 ion propulsion system was delivered just recently in December. Sorry if it's typo, December. But that's also currently here. And we conducted hot fire tests with our hardware in a thermal vacuum chamber prior to delivery. So it was very exciting to get many hours on the flight unit that we'll be firing in flight. And then this is our Mission Operations Center here at ASU, which we're partnering with Kinetics, which has done the mission navigation design for New Horizons and OSIRIS-REx, and ASU in partnership with Kinetics and Qualtech to do our mission operations ground data system development, which will all take place here in that room you see there. And this is a quick view. It's a little bit dated at this point of what our flat set bench looks like in our clean room. So you can see we actually can drive the spacecraft in an EM environment in our clean room. Now we have the flight hardware on the bench that's behind Patrick there, and we're starting to command everything on that bench. But all the components are laid out there so we can test all of our GDS system. I updated this slide just to show what the team is currently doing in terms of buttoning up the spacecraft and mechanical assembly, electrical INT of the flight unit. We're conducting some tests with some of the flight unit, the flight software, and command and telemetry processing. So we're on track to deliver the spacecraft by April, and looking forward to getting some updates on the Artemis 1 launch, but everything's on track currently with LunaH-Map for delivery to NASA later this year. We have a website. We currently installed a live webcam feed of our clean room. You're welcome to check us out and see what we're doing, and happy to take any questions.
Thanks, Craig. There was one question earlier on in your talk asking about the way that your satellite is going to be deployed. Is it a standard standard way that CubeSats are deployed? If so, can it mount to spacecraft in other ways, for example, with a traditional clamp band?
So because we're manifested on SLS, we are mandated to mount into or be deployed from the Planetary Systems Corporation deployer, which is mounted into the ICPS ring here underneath Orion. So the spacecraft is currently structured to fit into that specific deployer. So if there was a launch vehicle that could accommodate such a deployer, it would be possible to fit the LunaH-Map spacecraft within that. And that'd be the case for any Artemis 1 manifested CubeSat, to my knowledge. Does that answer the question, or?
I think so. Yeah.
Okay.
Are there any other questions for Craig? Or anyone from earlier speakers? Okay, so we've got 2 minutes before the next talk.